Hi everyone. So I will be presenting our accepted work from McKay about using reinforcement learning for automatic view planning. So first of all, why automatic view planning? So in clinical practice, to establish comparable metrics between different patients and to help the diagnosis process and compare between populations, the clinicians need standard views in order to extract these metrics. And this is, for example, in brain MRI, you have this mid-sagittal or axial or the four-chamber view in the cardiac imaging. This process can include several steps. And for example, to define the standardized views in cardiac MRI, these steps can include first defining the whole 3D volume of the image acquisition, like a pilot one, quick one, to know exactly where's the heart. Then define the left ventricle and then the short axis orientation, then the three-chamber view calculations and detect some landmarks in this view, then calculate the 2, 1, 4-chamber views. Similarly, but it's even like easier than the cardiac, the brain MRI, to define the axial plane, you need the anterior commissure points and the posterior commissure point, where you actually define the mid-sagittal plane based on the AC-BC line. And this includes as well landmark or manual interaction. So we can automate this method. This is what we try to do here. Why reinforcement learning? Probably most of you know about the work, the recent work in video games from DeepMind, OpenAI, and other companies or research groups that work with reinforcement learning. And they can solve a game or play a video game using an agent. They call this an agent who can interact with the environment, which is the game, and solve this sequentially and play the game till finish the target. Here we try to do the same thing. We have an agent that starts from anywhere to try to find the four-chamber view. This is the middle of the video. Yeah, start from here. There's a random plane, and it sees only this plane and try to find the four-chamber view the same way this agent interacts with this environment. We design an agent that interacts with a medical environment and try to solve the application using the same reinforcement learning algorithm. Quickly to recap before we go into reinforcement learning, in machine learning, we design algorithms that learn in data. So we have medical imaging task. We train the machine learning algorithm using the data from here to solve this task. And this can be categorized based on the data type or training data type in unsupervised, supervised reinforcement, or semi-supervised, as was explained before, or other techniques, or other categories. In unsupervised manner, you have the data, and you try to learn hidden patterns from the data, and there is no labeled data. And this is what you try designing an algorithm. But in supervised way, you have the label for this data. So you optimize the target or the output of the data. And this is what we do in segmentation or classification or different application. In reinforcement learning, there's an environment where your algorithm will interact with this environment by taking actions. So there's a step where the agent or that algorithm, compared to the previous ones, for the same scenario we took, so it will need to take a decision between two options or multiple options. And each one of them is an action. And based on this action, the environment reply with a reward during the training. And the idea of the agent or the algorithm is to maximize the amount of rewards it sees on the lifetime, which in this case, like just pick the action with the highest reward. And this is sequential decision making. So it's not only one step. And this is what makes it also different or compared to the other learning techniques or categories. This can be formulated as an agent, an environment. The environment provides a state to the agent take an action, then send it back to the environment. Based on this action, the environment gives a reward and a new state. And this reward could be positive or negative based on the action or the quality of the action the agent take. And this is mathematically modeled as Markov decision process. And each state and action also hold the Markovity property that they are independent of any previous state or action. So quickly, the main elements, this is the most important thing, is the policy, which is actually the strategy that the agents use to choose an action. And this is what we try to optimize at the end in the algorithm you're trying to design to solve the problem. And the solution is the optimal policy, which achieves the highest accumulated rewards. There's a reward signal that you take at each step, and this gives you immediate sense how good or bad taken action. While there's something called the value function, which is very important, and this is what include the reward or the steps that looks in the future. So this is include the accumulated rewards during the future. So to redefine reinforcement learning at the end is actually learning what to do or how to map situations to actions so as to maximize summation of numerical rewards seen over the learner lifetime, which we call policy. And there are different methods to solve this. We use Q-learning. It showed to be working in medical imaging, but there are also other methods that can be explored. So value functions, you can choose any value function. And the common thing between value functions, they should provide a value of one of the elements, either action or state or action independent of the state, or there are different ways that you can define it. It just needs to be intuitive or informative signal to the algorithm you design that you learn from. And it should show actually what's good and what's bad during the lifetime of the learning. And should be consistent as well, because the design of this one can affect your algorithm, or finally the solution at the end. Here we use the commonly one that used for Q-learning, which is called Q function. And this measures the quality of taking an action and at each state. So you are in current state and you want to take action, one from 4 actions, which one you take. And you give a quality of taking each one and how good each one is. And with of course, the optimal policy is the maximum of the whole accumulated rewards. The well-known DQN is actually applying convolutional network to approximate this function. So they use convolutional network to approximate the Q function. And there are several tricks that they use to make it work, but I will not go through them because we don't have time. But easily, it is just can be trained from end to end. These are the applications that used or applied reinforcement learning in medical imaging. You can see it has like most of our applications: segmentation, localization, landmark detection, image registration, and field planning, which is this work, which we will explain now. So now the second part is the field planning, how we apply this. So as we mentioned, it's a sequential decision process. So we want to solve or do the view planning in a sequential way. So we define our environment here as the 3D image scan. And we sample a state, which is a 2D plane randomly from anywhere. And this plane is parameterized using 4 parameters, this equation, which the first 3 is the direction of the norm of the plane. And the D here is the distance between the plane and the origin of your volume. And the action space is actually the change or the steps the agent can update the plane and move or navigate in the 3D volume or the environment. And these are as fixed steps in each or a single direction of each of these parameters. So we have 8 actions that should be taken at every step. There's important issue as well. So during training, you can, when you find the target plane, you know already during training the target plane, so you can terminate the training process. But while you are testing, you don't know the labels. So you don't know when to terminate the navigation process. And in this case, you can either use extra trigger action space or action value, and this is add the action space, increase it by 1, which can also increase the complexity of training. Plus, it doesn't trigger all the time. So you will need to define another hyperparameter, like how much you want or how many steps you want the agent to run till it terminates if it didn't find the target plane. While there was a classic paper that reinforcement learning without an explicit terminal state, this one, it gives you for free terminal state by oscillating around the right solution. So you don't have to explicitly include the external terminal state. And in this case, the agent will just oscillate around the target plane. And once it oscillates, you can terminate. But also we should mention when it oscillates, if it oscillates between 2 planes, which plane you should pick in this case. So we found that with our experiment, when the agent is far from the target plane, most of the Q values are very high, which means actually this agent is smart because it knows that it is far from the destination or the target, and it encourages the agent to go and just move action toward the solution. And if it is close to the solution, the Q values of most of the actions are lower, which means it discourages moving away from this area. So we usually pick with the lower Q value when it oscillates, which means that this state, it discourages me not to go out or take an action in this state. This is our terminal state that we use. We use also multi-scale agent. We need to capture bigger spatial relations in global neighborhood. And this is very useful in cardiac imaging when you have bigger field of view in the image and there is noise in the background. So if you use local information, you may get stuck in this noise and you don't reach the solution. And the problem here, when you increase the size of your network, of course, it would not fit the memory. So we use the multi-scale strategy, which is sampling with different voxel size. And we start from coarse to fine. So we start with coarse, like looking at a bigger image, and then smaller image by sampling with different voxel size. We use also hierarchical action steps, which means if you are far from or looking at the bigger size, you can move actually faster because you have bigger image now. And then when you get to the smaller fine-tuning final scale, you can actually move with smaller steps. So this is the pipeline. We have the input of our, this is the convenience of the DQN, and the input is the last 4 frames we have or in the lifetime of the agent or the deep planning agent. Then it feeds the network, and at the end we get 8 actions. Based on them, we update the new plane, sample a new plane, and feed it here and keep until it finds the target plane. We also designed the reward function as the distance between the parameters of the previous plane to the target plane, and also the distance between the current plane and the next plane. This gives me relative error, which could be positive or negative, and based on this, we get a reward. If we get closer, it will be positive. If we get further, we get negative. We use a couple of improvements, and this is double DQN, which fixed something in DQN, which is called the bias, because they use the same, or an old version of the DQN for the action evaluation with the action selection, and they just decorrelate this by replacing this here with the current new version of DQN. I didn't explain DQN, but I can explain further if someone asks afterwards. During DQN, it just decorrelate the action state in approximation, and by actually just easily splitting the value function, which only evaluates the current state without the function, without the action, an advantage function that evaluates action independent value without also the state. And the combination will give me the quality state function. So going to experiments quickly. We run 12 experiments using 4 different DQN-based architectures, and on 2 different set 3 target planes. We use for the evaluation 2 metrics, one of them the distance between anatomical landmarks projected on the estimated plane and the target plane, and the distance between them, which can give like anatomical meaningful distance, and the orientation of the norm between the ground truth and the estimated plane. During training, we start at random point. You just sample any random point in the 3D image and then sample a plane around this one, and in the direction of the norm between this origin and this point. And train 1 episode, which 1 episode will be the solution from the start or initial state till the terminal state, and do this many times. So first experiment, we run this on cardiac imaging to detect the 4-chamber view. We use 364 training, 91 testing, and 6 landmarks projected on our planes to measure the error. So here, this is the results. So the distance error of our agents, this is published work before in they use the multiple steps by defining landmarks, then fitting a plane to these landmarks. And they achieve this error, which is And our best agent here, which is the dual DQN, actually achieved better than this one. Even the error, the angle error here, you can see it's very high, which shows how difficult is the problem. And all our agents improve above this baseline. We also test on other data, which is a bit simpler than the cardiac imaging. When we detect two planes, the ECPC plane and the axial plane and the mid-sagittal plane. And here's some visualizations of the agents. You can see it starts from anywhere, either this example or this example, and try to find it. And this is the error at the end, which is between the landmarks. Okay. This is the final, like all the results from all the experiments. You can see that most of the agents perform similarly, the same performance, except that for the mid-sagittal, there's no significant difference. This one, the double DQN actually performs better than the dual DQN, and it's significant. Here's, well, the dual DQN works better for the cardiac, which makes sense that the value state in this bigger field view imaging is actually contribute to the results. Runtime, so it's a sequential solution. So wherever you start from, if you start from the solution, it will take longer. If you start close the solution, it will take less, much less. Each step takes like 0.02 with our implementation, can be improved. So if you take 100 steps to the solution, it will take 2 seconds to the target. It's very fast. Some challenges are the sampling noise. I'm not sure if it is obvious here, but you can see because you sample in different weird orientations, planes, you get actually like sampling errors with lines. And this is because of the sampling method. If you use more complicated one, it would be slower, but it can be more accurate. Also the field view and these lines, like if these lines sometimes is this orientation, sometimes like this, sometimes like this, and this is because of the image scans we have. But these are strands if we can get rid of them. Okay. There are some limitations to make it work. It is very difficult. It takes like some effort, especially in designing the small elements of the reinforcement learning. And also there is, as you have seen, there is no unique winner. So you have to test all of the agents, and this is also the same with Atari games. They have overall winner all the games, but if you check individual games, you will find that each method has different performance, and some of them are better than the others, but it's not the case for all of them. So to conclude, here we present like feasible reinforcement learning approach that actually achieve good results for a difficult application like view planning. And this can open direction for future improvement in this application or other application that we need sequential way of solving a problem. Future work, there are some nice ideas about using multi-agents, collaborative or competitive multi-agents to find the same plane or different plane at the same time. And also another good direction, but this is maybe far future, is including the expert in the process, where they can learn from the human, the same as AlphaGo when they play games with humans and they improve upon this. So here we can also learn some anatomical steps or like steps from experts who use anatomical information or background during their operation. There are some reinforcement learning references if you're interested. And at the end, I thank everyone from the Biomedia, and also the code is public. And I think this is by so far the only reinforcement learning open source for medical images. And there is 2 applications you will find there, landmark detection and view planning, if anyone wants to play around with it. Okay, thank you.